Good morning, everyone. We are Group 6 and we were assigned to discuss the topic gases. Here we have the OOTD or the objectives of the day, wherein at the end of this lesson, you, my fellow classmates, must be able to first, define pressure and give the common units of pressure. Second, use the gas laws to determine the pressure, volume, or temperature of a gas under certain condition of change. And lastly, is to use the ideal gas equation to calculate the pressure, volume, temperature, or number of moles of gas. But before the presentation of the mentioned objectives, let us first get to know gas. Now, what is gas? Gas is defined as an air-like substance that expands to fill the space it is in. Take note that gases are much less dense than liquids and solids. It is the phase of matter in which particles are usually very apart from one another, move very quickly, and aren't particularly attracted to one another. Gases are widely separated. It has no definite shape and volume. It has a low density and a high compressibility. It exerts pressure, it rapidly diffuses, and it expands when heated. Those that were mentioned are the properties of gas. Back to our objectives, let us define pressure. Pressure is equal to the amount of force per unit area as shown in this formula. Pressure exerted by a gas depends on the number of molecules present, the temperature of gas, and the volume in which the gas is confined. Common units of pressure: atmosphere or small letters ATM, millimeter of mercury written as small letters mm, capital H, small letter G, torr, Pascal or capital P, small letter A, and pound per square inch or small letters PSI. For this slide, we included the important conversion factors that we need to remember. 1 atmosphere equals 760 millimeter of mercury equals 760 torr. 1 atmosphere equals 101,325 Pascal or 101.3 kilopascal, and 1 atmosphere equals 14.7 pound per square inch. In the next slides, my groupmates will be discussing each gas laws starting with Boyle's law, followed by Charles' law, then Gay-Lussac's law, and lastly, Avogadro's law.
Boyle's law. The law discovered by Robert A. Boyle in 1662 is a basic law in chemistry describing the behavior of a gas held at a constant temperature. The Boyle's law states that for a fixed amount of gas held at constant temperature, the pressure of gas is inversely proportional to its volume. In symbols, it is also read as pressure is inversely proportional as the volume. The Boyle's law can be expressed using the equation pressure 1 multiplied by volume 1 is equals to pressure 2 multiplied by volume 2. Sample problem. A gas sample is observed to exert a pressure of 600 torr when confined to a 10-liter vessel at 27 degrees Celsius. What will be its pressure when the gas is transformed to an 8-liter vessel at the same temperature? Since we are looking for the P2 or the pressure 2, then we are going to use the equation pressure 2 equals pressure 1 multiplied by volume 1 over volume 2. Pressure 1 is equal to 600 torr and volume 1 is equals to 10 liters. Volume 2 is equals to 8 liters, so 600 torr multiplied by 10 liters over 8 liters is equal to 750 torr. So pressure 2, or the pressure when the gas is transformed to an 8-liter vessel at the same temperature, is 750 torr.
The next gas law that we are going to tackle about is the Charles law. This law came from the French physicist Jacques Charles during 1746 up to 1823 as he studied the effect of temperature on the volume of a gas at a constant pressure. This law states that the volume of a fixed amount of gas held at constant pressure is directly proportional to its absolute temperature, meaning to say that the quantity of gas and pressure remains constant, that when the temperature of the gas increases, then so does its volume and vice versa. This law can be presented in symbols like V proportional to T, where V stands for volume and T stands for temperature. In equation form, it can be presented as V sub 1, or first volume, over T sub 1, or the first temperature, is equal to V sub 2, or the second volume, over T sub 2, or the second temperature. Also, please take note that the absolute temperature refers to the temperature in Kelvin and not in degrees Celsius. Now let's look at this example problem. Here, a gas held at a constant pressure of 750 millimeters of mercury occupies a volume of 12 liters at 25 degrees Celsius. At what temperature in degrees Celsius will the gas occupy at a volume of 15 liters? First, we have to identify the given for us to fully understand how our solution will be. So here we have the first volume, 12 liters, first temperature, which is 25 degrees Celsius, and the second volume, which is the 15 liters. And by this, our goal is to find the gas second temperature as it occupies the 15-liter volume. But before that, just like what is stated in the previous slide, we have to convert first Celsius to Kelvin, since it's one of the vital rules for this law. 0 degrees Celsius is equal to 273 kelvins. Therefore, our first temperature will be equal to 25 plus 273, or 298 kelvins. Since our first temperature is set, let's proceed to the solution. Presented in the first box in the PowerPoint are the possible equations, which are mainly derived from the original one, which can help us as we solve for any specific Charles law related problem. And since we are going to find the second temperature, we are going to use the last equation presented, or the T sub 2 is equal to V sub 2 multiplied by T sub 1 all over or divided by V sub 1. Next, we are going to plug in the given from our sample problem. And here we have 15 liters times 298 kelvins divided by 12 liters. Cancel the liters. 15 times 298 is equals to 4,470 kelvins. Divided by 12 is 372.5. Bring down the sign K for kelvins and round off the value, and now we have 373 kelvins. Now, let's look back at the problem, and it says that at what temperature in Celsius will the gas occupy a volume of 15 liters? Therefore, by this, we are going to convert again Kelvin to Celsius, and it can be done through subtracting 273 from that value, and we have the result 100 degrees Celsius. And that's it. Our temperature as the mercury gas occupy 15 liters is equal to 100 degrees Celsius.
Hello, my name is William Drake Takaan and I'm going to present the Gay-Lussac's law. So in the early 19th century, a French chemist named Joseph Louis Gay-Lussac proposed two fundamental laws of gases. While one is generally attributed to a fellow countryman, The other is well known as the Gay-Lussac law. His daring ascents in hydrogen-filled balloons were the key to his investigations. So the Gay-Lussac law states that the pressure of a fixed amount of constant volume is directly proportional to its absolute temperature. So based on this illustration here, what can you say about it? So we have the temperature. So as the temperature decreases, the pressure also decreases. And as the temperature increases, the pressure also increases. So we can say that these variables, the variable P and the variable T, has a linear relationship. Why? Because as one variable increases, the other variable also increases. And as the one variable decreases, the other variable also decreases. So in symbols, we have this. So the P or the pressure is proportional to the temperature. So the Gay-Lussac's law can be expressed using this equation. So P sub 1 is over the T sub 1 equals P sub 2 over the T sub 2. So P sub 1 means the initial pressure. P sub 1 equals the initial temperature. And P sub 2 means the final pressure. And the T sub 2 means the final temperature. So to completely understand how to use this equation, I prepare a sample problem for you. So here's our sample problem. A 1 liter sample of nitrogen gas inside a metal container at 20 degrees Celsius is heated until its temperature is 95 degrees Celsius. The pressure inside the container is 20 degrees Celsius was at 3 atm. So atm means atmospheric pressure. So the question is, what is the pressure of the nitrogen gas after its temperature is increased to 95 degrees Celsius? So first we need to identify our given. So the initial pressure is 3 atm. Our initial temperature, so we need to convert it into Kelvin. So we need to add 273. So 20 degrees Celsius plus 273 equals 293 Kelvin. Our final temperature is equals to 95 degrees Celsius plus 273, and we will have 368 Kelvin. So our unknown is our final pressure, which is the P sub 2. So let's go ahead in our equation. So ano nga ba yung kailangan nating maging equation? So first, we need to cross multiply. P sub 1 times P sub 2 and P sub 2 multiplied by P sub 1. So next, ang mapapansin nyo ay bakit kaya naka-over siya sa initial temperature? So naka-over siya sa initial temperature because kailangan nating makuha yung final pressure. So para magawa yon, kailangan nating ma-eliminate sa kanan, sa right part, yung T sub 1. So after that, we will have, after natin ma-eliminate yung T sub 1, we will have P sub 2 or our final temperature equals the P sub 1 times T sub 2 over the T sub 1. So our solution. So we need to input our given or the given values in our equation. So the initial pressure is equals to 3 atm times the final temperature, which is the 368 Kelvin, over our initial temperature, which is the 293 Kelvin. So first, we need to multiply. 380 m multiplied by 368 A or Kelvin is equals to 1,104 atm multiplied by A. So pagkatapos nun, we need to divide. So divide it by 293 Kelvin. So 1104 atm times K divided by 293K is equals to, so ang equals niya ay 3.77 atmospheric pressure. So ang final answer, again, our final pressure is equals to 3.77 atmospheric pressure. That's the end of my presentation. I hope you understand the Gay-Lussac's law and its equation, and somehow how to deal problems involving this law.
The next gas law is Avogadro's law. Amedeo Avogadro was an Italian scientist known for his research on gas, volume, pressure, and temperature. He formulated the gas law known as Avogadro's law. Avogadro's law describes the relationship between the volume of the gas and the amount of gas molecules in moles. It states that for a gas held at a constant pressure and temperature, the volume of the gas is directly proportional to the number of moles of the gas present. So the Avogadro's law simply gives us the idea that the volume and the number of moles have a directly proportional relationship. That means that when your volume increases, the number of moles also increases, and when your volume decreases, the number of moles also decreases. The Avogadro's law can be expressed using the equation initial volume all over the initial number of moles is equals to final volume all over the final number of moles. Let's have an example. An 85 liters flexible container holds 3.4 moles of gas. How many moles of gas should be removed to decrease the volume of the container to 40 liters? Now let's write what we know. We have N sub 1, which is 3.4, we have V sub 1, which is 85 liters, and we have V sub 2, which is 40 liters. Now what we need to find is N sub 2. Using the equation, let's substitute the given. And after plugging in the given, to calculate the equation, we need to cross multiply. So let's multiply 85 liters to N sub 2, and that's gonna be 85 liters times N sub 2, and let's multiply 3.4 moles to 40 liters, and that's gonna be 136 liters times mole. Now let's divide both sides by 85 and cancel the same units, and we're gonna have 1.6 mole. Now let's go back to the question. The question asks, how many moles of gas should be removed to decrease the volume? So we started with 3.4 moles and we ended with 1.6 moles. So how many moles of gas was removed to go from the starting value of 3.4 moles to the final value of 1.6 moles? To find this, we need to calculate the change in moles. That's the final amount minus the initial amount. The final amount was 1.6 and the initial amount was 3.4. So 1.6 minus 3.4 give us negative 1.8 mole. And that's the final answer.
And down to our last topic, which is the ideal gas equation. But before anything else, let me first define what is an ideal gas. An ideal gas is a theoretical gas composed of many randomly moving point particles that are not subject to interparticle interactions. Its molecules occupy negligible space and have no volume. The ideal gas equation is derived from taking and combining three of the gas laws discussed in the previous slides, including Charles' law, Avogadro's law, and Boyle's law. In this equation, we make relations between the gas's pressure, volume, temperature, and quantity of moles. So, this is the equation used in an ideal gas. PV is equal to nRT, where P is the pressure of the ideal gas, V is the volume of the ideal gas, N is the amount of ideal gas measured in terms of moles, R is the gas constant, which has the value of 0.0821, and T is the temperature. Let's take a look at this example. A 2.5 liter container holds 0.45 moles of nitrogen gas
at 315 Kelvin. What is the pressure inside the container? So starting from the given, volume is equal to 2.5 liters, N, which represents the number of moles, is equal to 0.45 moles, and T, which stands for temperature, is equal to 315 Kelvin. So we simply use the formula is equal to nRT. Substitute the values and then solve. So P times the volume 2.5 equals N, which is 0.45, times R, which is 0.0821, and times T, which is 315. Now let's multiply. 0.45 times 0.0821 times 315 is equal to 11.64. And now, we're going to divide both sides by 2.5 to get P by itself. So 11.64 divided by 2.5 is gonna give us a pressure of 4.66 atm. And that's how we solve an ideal gas equation. That will be our presentation on the topic gases. Thank you for listening.